In continuation of what we have done in the previous class, we were looking at how to analyze the growth of boundary layer on a flat plate in laminar flow. The objective of that exercise was to obtain delta, the thickness of the boundary layer, as a function of axial distance, that is the distance along the length of the plate. And we have also seen that inside the boundary layer the flow is two-dimensional. Outside of the boundary layer the flow is inviscid in nature, such that Euler's equation, Bernoulli's equation, is applicable. However, inside the boundary layer the complete Navier-Stokes equation has to be solved in order to obtain the profile of the thickness of the boundary layer as a function of x, where x denotes the axial distance. We from our basic understanding of the physics of the process, we have done some analysis based on which is going to be a significant term in Navier-Stokes equation and which is not. First of all, we have assumed that it is a zero pressure gradient flow, and since the plate is horizontal, there would be no effect of gravity. So it's a two-dimensional flow where the velocity Vx, velocity components Vx and Vy would be functions of both x and y. The plate is wide in the z direction, therefore the z dependence of velocity does not appear in our analysis of Navier-Stokes equation. So we have four terms in Navier-Stokes equation. The first two on the left hand side, as we have seen before, these two terms essentially they refer to the convective momentum, and this is the conductive or molecular transport of momentum. And using the boundary layer approximations, what we have seen is that Vx is relatively large compared to Vy, because the principal motion is in the x direction. However, since the thickness of the boundary layer, which is denoted by the dimension is denoted by y, since the gradient of the variation in velocity with respect to y is large in comparison to the gradient of velocity with respect to x, none of these two terms can be neglected, can be equated to 0 based on simple heuristical analysis. However, if we come to the right hand side, this denotes the molecular transport of momentum in the y direction, and this is molecular transport of momentum in the x direction. Since the gradient of Vx with respect to y is large, it is expected that the transport of momentum, molecular momentum, in the y direction would be much more than the transport of molecular momentum in the x direction, since the gradient of velocity in the x direction is small. So based on our idea about the gradient of the x component of velocity in the y direction and in the x direction, it is safe to say that the gradient of the molecular transport of momentum in the y direction would be much more than the molecular transport of momentum in the x direction, which leads us to the governing equation. And we understood that there would be no slip at y equals 0, and at the edge of the boundary layer or beyond the boundary layer, when y, mathematically speaking, when y tends to infinity, the velocity would simply be equal to the free stream velocity, that is velocity outside of the boundary layer. And at the x equals 0, the Vx, that is the axial component of velocity in the x direction, would simply be equal to u, where u is the approach velocity. And we also understand that for a flat plate, v, the approach velocity, would be equal to u, the free stream velocity. So therefore we can simply write Vx equals u. In the next step, we have proposed, which the solution is by Blasius, where he reasoned that the dimensionless velocity profile, when plotted against a dimensionless distance from the solid wall, would be similar for all cases. And this eta, which is the dimensionless distance from the solid wall, is expressed as y by delta, where delta is the local thickness of the boundary layer. However, we understand here that this delta is a function of x, as we progress in the x direction, the delta keeps on increasing. So therefore, his reasoning, Blasius's reasoning is that, which is supported by experimental data, that dimensionless velocity profile would be similar when plotted against a dimensionless distance from the solid wall. So with this, then we have two equations to deal with. The first one is equation of continuity and the second is equation of motion. If we introduce a stream function, then because of the property of the stream function, the first equation, that is equation of continuity, gets automatically satisfied and we are left only with the equation of motion. This equation of motion, and using the method of combination of variables which we have discussed in the previous class, we are hoping that this PDE can be transformed to an ODE, and that's essentially the method of combination of variables, and we would see whether it would work here in this specific case or not. And since we are expressing everything in dimensionless form, so instead of a stream function, we are introducing a dimensionless stream function denoted by f, and we understand that this f is a function of eta, the dimensionless distance from the solid wall, and this is how the dimensionless stream function is expressed. So we do not deal with Vx, Vy anymore. We rather deal with psi, which is a stream function. Since psi, we know what would be the expression for Vx if we know psi, and since it's dimensionless equation, we also do substitute psi with a dimensionless stream function. So therefore, f eta is a function of eta, and we are hoping that this PDE can be transformed to an ODE when instead of Vx, del x, Vy, del Vx, del y, and so on, we introduce the dimensionless stream function, and instead of x and y as the independent variable, we will bring eta as the independent variable. So if we are correct, then our final equation would contain f and eta. So if it contains f and eta, and if we understand that f is a function only of eta, then the governing equation between f and eta will simply be an ODE. So this is what we have done in the previous class, and based on an approximate solution of the equation near the edge of the boundary layer, where we have seen what would be the orders of magnitude of these various terms, we also have defined that the dimensionless distance, or rather the combination variable which contains both y and x, should be of the form where eta equals y root u by nu x. This is the kinematic viscosity. So with this and with our definition of f and eta, we would see whether this equation can now be transformed to an ODE. So we start from that point, and what we first do is, using the definition of Vx, which is del psi by del y, and I would write here how we have defined eta. This is how we have defined eta, and I would show you just one example, and the governing equation is Vx del Vx del x plus Vy del Vx del y equals kinematic viscosity del square Vx by del y square. So this is the governing equation. We need to substitute each of these terms in terms of psi, or in dimensionless form in terms of eta. So I'll show you just two examples of how to get the expression for Vx and Vy, and the expressions for del Vx del x, del Vx del y, and del square Vx by del y square are given in the textbook. And for this part, I am following the book of Fox and MacDonald. So if you see the book by Fox and MacDonald, Fluid Mechanics, which is one of the textbooks for this course, the complete derivation with all its particulars would be clear to all of you. So we are trying to right now find out what is going to be the expressions for Vx, Vy and all other terms in the equation of motion in terms of psi, the dimensionless dependent variable, and eta, the dimensionless independent variable. The expression for eta we have already obtained based on an order of magnitude analysis. So I am going to show you how to get the expression for Vx and Vy. The other terms of the equation of motion can be seen from the textbook Fox and McDonald. So let's see how we do Vx in this case. So from definition we can simply write this, and if we introduce, and the f is defined as psi by root over nu x u. So if we do this del psi by del y, if we transform that psi to f, it would simply be equals nu x u times df by d eta. See that since f is a function only of eta, the combination variable, I am getting rid of the partial sign and I am simply getting ordinary differential equation, ordinary differential form in this. So it's df d eta and not del f by del eta. And if I find out what is del eta by del y from over here, I would simply get as u by nu x. So this directly follows from our definition of eta. So therefore this expression is u times df d eta. So my Vx therefore is equals u times df d eta. This can subsequently be substituted in here. Similarly, when we start with Vy, which is by definition of stream function del psi by del x, I can write it as minus del x. Instead of psi I am going to write here as nu x u, which can then be expanded as so this is just an expansion, and when we continue with the derivation of this, what you would get Vy from the previous page it's simply just a substitution of the independent variables. So instead of del f del x, I simply writing df d eta, since f is a function only of eta. I'll simply write the final step, since it's given in a nice form in the equation in the textbook. So this is the expression for Vy, and from previous slide we have seen Vx is equal to u times df d eta. The expressions for and the governing equation as we have seen before is del Vx del x So I can substitute the expression for Vy in here, the expressions for Vx in here. All these, the remaining terms can also be evaluated, which I am not showing in here, but it's given in the textbook. So I'll leave that out, and what it turns out, what it would result in is this as my governing equation. So this is going to be the governing equation. The major thing that one should first see is this is an ODE. So we are successful in transforming this PDE to an ODE by invoking the definition, by invoking a stream function, by using through the use of a combination variable eta that contains both x and y, and a judicious selection of the expression of eta from an order of magnitude analysis enables us to convert the PDE to an ODE. However, if you look at the PDE, look at the ODE, it's a nonlinear ODE of higher order terms. So even though we could get an expression or a neat governing equation, ordinary differential equation for the growth of boundary layer for the simplest possible case, which is flow over a flat plate, it is still impossible, not possible to obtain a closed form solution. So even though we have the governing equation, we know what are the boundary conditions, a solution to this is not possible using analytical methods. So numerical methods will have to be used, was used by a researcher named as Howard, and what he has presented is he solved this equation numerically and presented a table containing in the column, first column is values of eta, corresponding values of f. The next column contains the value of f prime, which is df d eta, f double prime, and so on. So looking at the table, the numerical solution of the governing equation with appropriate boundary conditions, you generate the results table. But the results table in itself is quite informative, and it would give us a form, a compact form of the growth of the boundary layer. Or in other words, the first thing that we started this exercise is to obtain the relationship of delta as a function of x. So this table can now be used to obtain this functional form of delta in terms of x. So that's what we would see next. So we are starting with this equation, the governing equation. We also know that eta is defined as, and we have seen the expressions of Vx to be equals df d eta, and the expressions for Vy to be equals half these are the expressions that we have seen. So we will use this later on. We also understand that the boundary conditions to solve this equation are at eta equals 0, that means eta equals 0 means y equals 0. At y equals 0, we understand that Vx is going to be equal to 0. So if Vx is 0, then df d eta must be equal to 0. I would repeat it once again. At eta equals 0, the first condition at the liquid solid interface, that means at y equals 0, the velocity in the x direction due to no slip condition must be equal to 0. So if velocity in the x direction is 0 at eta equals 0, which essentially tells me that df d eta would be equal to 0. So df d eta would be 0. That's my boundary condition. I also understand that due to the same no slip condition, not only Vx should be 0 at eta equals 0, Vy would also have to be 0 at eta equals 0. So when you have a no slip condition, both components of velocity, that is the Vx and Vy, would be 0. So if both Vx and Vy to be 0, then from the expression of Vx I have obtained that the necessary boundary condition is f prime, or rather df d eta, to be equal to 0. Now let's look at the expression of Vy to see what would the no slip condition on Vy would give me the value of either f, f prime or f double prime to be used as a boundary condition to solve this problem. So let's look at the Vy. At eta equals 0, that means at y equals 0, I understand that this is 0 since my Vx is 0, which I have already obtained. So at Vy to be 0, since this is 0, this term must also be 0. So it's simply going to be not only the gradient of f with respect to eta is 0 at eta equals 0, which directly can be seen from the expression of Vx, the requirement that Vy will also have to be 0, and since df deta is already 0, f must also be 0. So the boundary condition, no slip boundary condition, would be f equals 0 and df deta is also equals 0. And the other boundary condition, when eta is infinity, that means y to be very large, and when y is very large, Vx approaches or Vx becomes equal to u. So at a point when eta tends to infinity, which physically represents a point far from the solid plate, the velocity of the fluid at that point would simply be equal to the free stream velocity. So the form of the equation for Vx would tell you that the df deta, since Vx is equal to u times df deta, since Vx and u are equal at that point, you simply have df deta to be equal to 1, which would constitute the other boundary condition to solve the problem. So to solve the ODE. So for this third order ODE, now we have three conditions. One is the no slip, that is at eta equals 0, both f and f prime are equal to 0, and at the other end, when we are far from the flat plate, since Vx is equal to u, I am simply going to get f prime is equal to 1. So these are the three boundary conditions which Haworth has used in order to obtain a numerical solution of the governing differential equation. So at eta equals infinity, f prime is going to be equal to 1. Now the table that he has provided is eta, then f prime and f double prime. I'll only list some of the values in here. The rest you should be able to see in your textbook, and I would only write those terms which are going to be relevant for our subsequent analysis. But he has given a detailed list of values of f double prime and f prime and f double prime for different values of eta. But I would list only some of the values, 4 or 5 values of this table. So this turns to be 0, this is 0, and this would be 0.332, and 5.0, 3.28329, 0.99155, and 0.01591, and some other values which we would subsequently used in a tutorial class. Almost 1, this is almost 1, okay. Let's look at these values. These are from the numerical solution of Haworth. So if you look at the definition of Vx, you understand that V and Vx to be equal to u, f prime has to be equal to 1. So the definition of Vx tells you that in order for the velocity to approach the free stream velocity to be equal to the free stream velocity, the value of df d eta must be equal to 1. Now, if you recall the definition of the age of the boundary layer or the thickness of the boundary layer, we have said that it is that point at which the velocity reaches 99% of the free stream velocity. So, let us see where we have this 99%. It is at this point. So, at this point the f prime is about 99%. So, therefore, Vx by u is equal to 0.99 and therefore, it reaches 99% of the free stream velocity. And where does it happen? When eta is equal to 5. So, I will write that eta equals 5 where f prime is equal to 1 can be written as the age of the boundary layer, can be taken as the age of the boundary layer. So, let us see how does that help us. We understand that by definition eta is y root over u by nu x, and eta equals 5 can be taken as the age of the boundary layer. So, if that is so, then at that point when eta is 5.0, this y would simply become equal to delta, where delta is the thickness of the boundary layer. Once again, for value of eta, we have seen f prime is equal to 0.991. So, that is the velocity Vx by u is equal to 0.99. So, velocity reaches 99% of the free stream velocity, and at that point y must be equal to delta. So, you have an expression for delta from here as 5.0 pi root over u by nu x, which can be slightly modified, slightly changed. This is Rex, it is just a reorganization of the terms and nothing else. So, what you get is delta to be equal to 5.x by root over Rex. So, this term, this expression tells you what is the thickness of the boundary layer at a given axial position. So, if you have the growth of the boundary layer, if you fix the actual position which is x, you know exactly from this closed form equation what is going to be the delta at that point. So, we have achieved one of our goals, that is to obtain the thickness of the boundary layer at any given axial position. Let us quickly look at some other important parameter which the engineers would like to have, which is to opt what is the shear stress exerted by the moving fluid on the plate, or in other words, what is the wall shear stress. Can we use the numerical solution of Howard to obtain such a closed form solution for the wall shear stress as well? So, we will quickly do that. The wall shear stress is simply, which I denote by tau w, is mu del Vx del y at y equals 0, which can be written as del y. Instead of Vx, it is del psi by del y at y equals 0. Now, if I bring in instead of y the concept of eta, the combination variable, it is del y of u df d eta at eta equals 0. So, after a bit of substitution which you would be able to see in your text, it would simply be equals to mu times u root over u by nu x times d2f by d eta square at eta equals 0. So, this is the expression for wall shear stress, and the only thing unknown in here is what is the number d2f by d eta square at eta equals 0. I bring in this. So, d2f f by d eta square, which is nothing but f double prime, for the value of eta to be at equal to 0, f double prime is simply equals 0.332. So, the numerical value of this is simply equals 0.332 from the numerical solution of Haworth. So I'll bring in this 0.332 over here, and what would I get since at eta equals 0, f double prime to be equals 0.332, what you would get tau w to be equals 0.332 u times root over rho mu u by x and equals 0.332 rho u square by root over r e x. So once again I write here the expression of tau w to be equals 0.332 rho u square, where u is the free stream velocity, by r e x. That is another compact expression for the wall shear stress, and sometimes we define a shear stress coefficient which is traditionally denoted by Cf. By definition, Cf is wall shear stress by the dynamic pressure, and therefore if you bring in the expression of tau w in here, what you would get is 0.664 by root over r e x. So the three equations, three conditions, three expressions that we have obtained are through this exercise are these three. One is, the first is an expression of the boundary layer thickness. The second is an expression of the wall shear stress, and the third, which is just by definition more commonly known as the shear stress coefficient. These two are equivalent. These two are equivalent is an expression for the shear stress coefficient, which is 0.664 by root over r e x. So one can see then that through the use of Navier-Stokes equation, boundary layer approximation, identification of the appropriate boundary conditions, evaluation of a combination variable which combines both y and x into eta through an order of magnitude analysis, introduction of stream function and a dimensionless stream function, all these complicated steps are necessary to convert the Navier-Stokes equation inside the boundary layer, for two-dimensional flow inside the boundary layer, to an ODE. But even that ODE is nonlinear ODE, and it is higher order as well. So no analytical solution was possible, and one had to use numerical solution techniques to obtain the results, which is for any value of eta, what are the values of f, f prime and f double prime. And since we know how would the velocity Vx, velocity in the x direction, behave when we reach the edge of the boundary layer, and what would be the gradient of the velocity at y equals 0, that is on the solid plate, we finally got expressions of delta as a function of x and tau w or Cf, the friction coefficient, as a function of x and other flow parameters, the physical property of the fluid and so on. So for the simplest possible case, it is complicated. Okay. So this method can be used for flow over a flat plate, but this approach cannot be used for any complicated geometries. This is only limited to laminar flow. So if the fluid is undergoing or in turbulent flow, this expression cannot be used. This is for a zero pressure gradient flow. If you have a pressure gradient present in the system, because of suppose it's not a flat plate, then this approach cannot be used. So we have a solution, but the solution is for the simplest possible case, and it cannot be termed as a general solution or an easy to use approach in solving the boundary layer parameters for any type of flow on any geometry or any type of surface, any geometry surface. So there has to be a generalized method which is easy to use and is not restricted by all these constraints. So what we would do in the next few classes, after I solve one problem, a tutorial class on this, is to show you a generalized approach in which it would be far more easier to handle situations which are not so-called the ideal systems, flow over a flat plate. It would be approximate, but it would still allow us to compute these numbers, the growth of the boundary layer, the value of the wall shear stress, and so on, in a much more effective and easy to use way. So that is what we would do in the next class.